Alrighty, so today we're going to continue working through thermodynamics. Last time we finished up calorimetry. We talked about, of course, specific heat, Cm delta T, the equation that allows you to figure out how much heat is transferred by changing the temperature of an object. We also talked about latent heat, which is how much heat must be transferred to an object to change its phase, so to melt or sublimate or boil, things like this. Well, now we're going to talk about how heat is actually transferred to objects. We've just kind of accepted and taken for granted that we can transfer heat from one object to another, but we'd like to investigate the mechanism, the methods for how we can transfer this heat energy. And so, to start with, we must know that there are three ways to transfer heat. And they are conduction, convection, and radiation. So, when an object gives heat away or takes heat in, it must do it in one of these three ways. So what is conduction? Conduction is when heat is transferred between two objects that are touching. They're in physical contact. So, for instance, if you have a very hot piece of metal and you grab it, well, that heat is conducted from the hot metal into your hand, into your skin. If you have, for instance, let's say a very cold glass window, especially right now, the way the temperatures have been the last few days, pretty cold. If you were to touch your window, it would feel extremely cold. And the reason is because heat will be conducted from your warm hand into the cold glass. That's conduction. It must be done through physical contact. And when it's done through physical contact, that is called conduction. Convection. The best way to think about convection is to think about a convection oven. If you've ever, I'm sure many of you have heard of convection ovens, but if you don't know what a convection oven actually is, it's a regular oven that you'd have in your kitchen, but it contains a fan on the inside of the oven, or a series of fans. And what the fan does is it blows the hot air to circulate it around inside the oven. The reason being, normally, because of how imprecise ovens are created and how the heating elements are arranged in different ovens, you may find, if you have a regular oven or you don't use the convection feature, that maybe one side of the oven is hotter than the other. So let's say you're baking some cookies, you put the pan in. If you don't spin the pan around halfway through, you may find that the right side of the cookie, or the right side cookies on the pan, are darker than the left side, or vice versa. Or maybe, one corner of the oven, so maybe the back left corner is hotter than the front right corner, and so on. So it's not equal temperature all around. There are hot spots and cooler spots. Well, by placing a convecting fan in the oven, the heat is circulated around, balancing it more, making it more equalized. And in theory, every part of the oven should be at the same temperature. That's what convection is. It is circulating the medium, whether it's the air inside of the oven or if this is cold water or hot water, and you're mixing the water together. As the water mixes, it kind of equalizes. Or in a star, for instance, there's different parts of the star at different temperatures. And if you're thinking about the sun, there's these convection loops where the very, very hot interior rises up through the material of the sun and creating kind of vertical whirlpools where this heat is circulating around. These are convection. So, as I said, it's easy to think of an example, less easy to define it precisely, but basically it is when the heat is circulated by the motion of the medium. Like I said, whatever medium is holding this energy or moving the energy around, it could be water, air, whatever it is, its motion around, circulating around, is moving heat from one spot to another. The last, radiation, a good way to think about this is, let's say you turn on a lamp and you leave it on for a little bit, and then you go put your hand close to the light bulb. Not touch it, but just put it close. You feel the heat coming off of the light bulb. You can feel that it's warm. And the closer you get, the more, the hotter it starts to feel. That's radiation. It's basically the transfer of heat by giving off energy in the form of light. And when I say light, you must understand I don't necessarily mean visible light. You know, I use the example of the light bulb. I don't mean necessarily that we're talking about the fact that it brightens the room. What I mean is that's part of it. That's why a light bulb lights up, especially the old incandescent style. You would have energy or a current flowing through the wires. It goes into a filament, and it creates a lot of friction, let's say, in the filament as the electrons try to pass through. This friction causes heat. It builds up heat, and it gets so hot that the filament actually turns bright red and then yellow and white. And that's the light that lights up your room. So the light that's given off because an object has excess energy, this is radiation. And so that's why light is called electromagnetic radiation. But it's more than visible light, as I said. It also includes things like thermal radiation, infrared, or ultraviolet. All of these things are forms of radiation, forms of light, which allows heat, energy, to transfer from a hot object to colder surrounding objects. So those are the three ways we can transfer heat. By touching, physical contact, this is conduction. Convection, the circulation of the material with the heat built into it. Or radiation, something gets so hot that it gives off light, and thus that energy is escaping from the hot object into whatever surrounding objects, the air, the environment, or your eyes, or your skin, or whatever. So we're going to investigate these in a little more detail. The first one we're going to investigate, of course, is conduction. And that'll be the point of this particular video. What can we do with conduction? We understand what it is, of course, theoretically or intuitively. Conduction is when you make physical contact with something that's hot or something that's cold. heat is transferred from one object to another because of the physical contact. But of course, as physicists, we want to actually be able to solve problems. How does this help? What's important about this? Can we make predictions? Things like this. And indeed we can. We can figure out how much energy is exchanged per second, so we can figure out the power, but how much heat exchanged per second by conduction. So you put one object in contact with another, heat will move across from the hot to the cold until they get to an equilibrium temperature, so everything's at the same temperature, let's say. And we could figure out how fast this heat is moving. That is, 100 joules per second leaves the hot to go to the cold. Let's, as an example. The equation we're going to use goes like this. Q over T, which we could call the heat transfer rate. So how many joules per second, how much energy per second flows, is equal to a factor called K, where K is called the thermal conductivity, which basically says how easy does this particular material give off energy. Obviously, if you have, for instance, a styrofoam cup and you touch it, it doesn't really transfer energy. It doesn't feel cold, it doesn't feel hot. But if you have a metal pipe or a hot metal pan or something like that, well, it'll either feel very cold or it'll feel very hot depending on its temperature. That's because metal is very conductive. It loves to move energy back and forth. So the thermal conductivity kind of tells you about what material we're talking about. Are we talking about glass, like a window? That may be interesting if we want to figure out what kind of windows we should buy for our house, how thick they should be, what material should they be made of, so that our house stays cool in the summer and stays warm in the winter. If you have very poor windows that have a very high thermal conductivity, then those windows let heat in or let heat out very easily. But if you get very good insulating windows, their thermal conductivity are very low, and thus energy isn't transferred from the inside to the outside or from the outside to the inside, and so the inside of your house stays at a normal temperature quite easily. So generally this is something given in the problem. The K for glass is, 500 or whatever. That's what K is. What else should this depend on? Well, think about it. If I'm going to give energy from one object to another, and I'm talking about how much energy is going to flow per second, it should depend on how much physical contact there is. In other words, if I put my hand on a glass window and it feels cold to my hand, well, the amount of energy that's going to leave my hand should depend on how much of my hand is touching the window. If my whole hand is touching it, then a lot of energy can leave. But if only one little finger is touching it, then there's only a little bit of my hand that can give off that energy. So it should depend on how much physical contact, and that's called the area, A. A being the cross-sectional area, the surface area, I should say. Let me call it surface area to not confuse things. The surface area that's in contact. It should also depend on how big of a difference in temperature there is between the two objects. So, for instance, if the window, the glass, is pretty much the same temperature as my hand, well, that energy isn't sucked out of my hand all that hard. It's just kind of leaves at a nice slow pace. But if the window's extremely cold, then that glass really wants to take in energy in a hurry. It wants to warm itself up. So the energy will leave my hand very quickly. Same thing, for instance, with, let's say, a glass of water. If you have a glass of water that's hot and you put some ice in it, though the ice and the water are in physical contact, so heat is conducted out of the water to melt the ice. Well, we can see when we do this, the ice melts very, very quickly. However, if you have a cold glass of water and you put some ice in there, that ice takes a very long time to melt. So obviously, the amount of heat that could leave the object to go to another object will depend on how big of a difference those two objects are in temperature. So it should depend on delta T, the difference in temperature. Temperature. Okay. And finally, one more term, and that is the thickness of the objects we're talking about. We already talked about the cross-sectional area, so how much contact there is. But let's say there's a very thick window versus a very thin window. Obviously, a very thin window can only take up so much energy before it warms up. But if I have a very, very thick window, then there's a lot of material there that could soak up energy. Thus, the thickness of the material should also come into play, and the way it comes into play is in the denominator as a letter L. L is the thickness. And that's our equation. And so with this, we'll be able to work a few problems, figuring out how fast or how much heat is lost or transferred, or however you want to say it, per second, or maybe we can say how much heat is transferred from the first object to the second after 4 hours. You know, that's what the little t down here, this t, is time. So it depends how we ask the question. If we want to know the heat transfer rate, we're looking for Q over T. It's just a thing called Q over T. Or if we want to know how much energy per second is lost, we're looking for Q over T. If we're looking for how much heat is transferred in a certain period of time, like how much heat would be transferred in 2 minutes, then what we would do is we would take this equation and then solve for Q instead, and it'd be K A delta T over L times little t, where little t now is some time given in the problem. So there's two ways. I mean, it's the same equation, obviously. It's just t is on one side or the other, depending on what the question will ask us. So let's try an example. Let's take this example here. Let's say we have a glass window which is, let's say, 5 centimeters thick and has a conductivity of 250 joules, joules per meters, seconds, Kelvin. I think that's the units. Don't worry about the units so much. but it has a conductivity of 250. If the window has a surface area of, let's say, 2 square meters, how much heat is transferred per second from the outside temperature of 90 degrees C to the inside at, let's say, 70 degrees C. Now, obviously, 90 and 70 degrees Celsius are extremely hot. I'm just using these numbers. First of all, they're nice round numbers, and also it sounds like Fahrenheit numbers. Don't mind the fact that if it were 90 degrees Celsius outside, we'd nearly be boiling. This is our question. We have a window of a certain thickness. It's a certain material, so we know its conductivity. If the window is so big, 2 square meters big, and we know the outside is at 90, whereas the inside is at 70, I want to know how much heat is transferred per second. Okay, find the heat transfer rate. All right, well, first of all, let's go ahead and draw a little picture. This will help us. Let's say this view I'm looking at, this little box I drew, pretending it's the edge of the window. So I'm looking at its side. Here's the outside. Here is the inside. Okay. And so again, you're looking at the side of the window, not the face of the window. So the thickness of my window here was given as 5 centimeters. So that's 0.05 is the thickness. Let's say the area was 2 square meters. That's given in the problem. And the conductivity K is 250. I want to use the equation Q over T, the heat transfer rate, is K A delta T over L. So what do I need? Well, I need K. Well, I have it. It's 250. I need the surface area. I have that. That's 2. I need L. That's the thickness. That's 5 centimeters. And I need delta T, where delta T, of course, is, we could call it final minus initial, or we could call it T2 minus T1, or T outside minus T inside. These are all different labels for the same thing. We want the difference in temperatures between one side and the other. Which one you call T2 and which one you call T1 doesn't matter. If you label it the other way, you'll get a negative sign, and it just means heat moves the other way. It's all the same thing. But when you see delta T here, all you need to know is it means the difference between one side and the other. Okay, so let's call T out minus T in. So, I have that. I know that. T out, that's 90, and T in, that's 70. Good, I have all the information I need. I just plug my numbers in. K, that's 250. A, 2 square meters. Delta T, so that's outside minus inside, or left minus right. Over the thickness of the window, needs to be in meters, so it's 0.05 meters. And then all I have to do is stick this in my calculator, and I get 200,000 joules per second. So that's a lot of energy moving through our window. So, as I said, if this is our house and this is a window in our house, we want to make sure to get a window with a K value as small as possible. Because the bigger this number is, this 200,000 we just got, the bigger the heat transfer rate, the more energy is going to move into our house. So on a hot summer day, the more energy coming into our house, the hotter our house is going to be. So our AC has to work even harder to keep us cool. Whereas if we get a window with a very low K value, then much less energy will move through our window per second, and our air conditioner can keep up. Anyway, this is a little example, show you how the equation works. As you can see, it's not that hard. It's a basic equation, plugging the numbers that we have in our problem. You just have to know what each term means, and it's fairly straightforward once you have that. Now, next time, I'll do a video with some more examples, and we're going to see some examples where maybe we have two things in contact. So you may have, let's say this is the outside, this is the inside, and perhaps this right here is glass, and maybe this is some other material, maybe drapes, or like, window drapes. And so how about the energy flowing through that system, a dual layer system? How can we handle the fact that there's not just one material with one K value, there's now two materials? So we'll see how to do that problem. It's going to turn out that we use the same equation, we just have to use it twice. But anyway, for now we're concentrating on conductivity. You'll see in a video with some more examples, and next time, the next lecture, we're going to talk about radiation. Convection, that is a method where you need to know the intuitive, conceptual part of it, but we're not going to have any equations or anything associated with it. So we're only going to have equations for conduction and radiation. Right now we're doing conduction. The next lecture will be on radiation, and you'll see that one next time. So I hope this was clear, and until then.